All right, and we are back, and now we are going to define our engineering definition and our tensorial definition of strain. So we previously defined normal strain, but just a little reminder, change in length over initial length. And again, it's still a tensor property as well. So it's going to have a second rank tensor property because we have to have basically, you could actually prove this through an argument of energy conservation because this is the parameter that links these two, so this must be a second rank tensor property as well. And it's actually a linear algebra proof that you can also do, but we will not do here because this is not a linear algebra class. But we have not, as of yet, defined engineering shear strain. So shear, as we've seen in shear stresses, you're going to shear the material, and we can see this example of pure shear here. So if I deform my material, you can see here's my shear here, and I could define the shear as the change in length, in basically, so this would be my gamma over 2. So it's a change in length here divided by this original length as well of my material. So it's this kind of transverse displacement, again, because in our notation, I and j are not equal as well. So you can kind of look at shear here, just like in normal stresses, there's going to be a proportional Hookean type law relationship between shear stress and engineering shear strain. But here's where the problem arises. Actually,